Welcome to lecture 32, where we start a new chapter, numerical series. So let's give a definition of numerical series. Let an be a sequence of real numbers. We define the sum for k goes from 0 to infinity of ak, which is nothing else than the sum of all the element of the sequence as the series. So this is the series corresponding to the sequence an. We also define the concept of partial sums. And a partial sum is indicated with s subscript n, is nothing else than the sum of the first n plus 1 elements. So this is the sum for k goes from 0 to n of ak. So it is a0 plus a1 plus ... up to an. And you see that these are clearly n plus 1 elements of the sequence. So this is just a finite sum. And now we are ready to define the fundamental idea of sum of the series. So what is the sum of the series? Well, the sum of the series, which is indicated with the sum k goes from 0 to infinity of ak, is defined to be the limit as n goes to infinity of the partial sum as n. And we have 4 options, just like we had 4 options for any limit. So we have option 1, Sn tends to a finite real number L, and in this case we say that the series converges to L. Type 2, Sn diverges to plus infinity, and we say that the series diverges to plus infinity. Type 3, Sn tends to minus infinity, so we say that the series diverges to minus infinity. And type 4, Sn has no limit, and we say that the series is undeterminate. Okay, so we have this list of 4 options, just like we had with the limits. In fact, so this is the idea. The sum of the series is defined as a limit, so we are falling back into one of the definitions of the limits. So what is the operative procedure to determine the sum of a series? Well, we'll start from the sequence an. We find the partial sum as n, and then we determine, if possible, the limit as n goes to infinity of Sn. So let's provide a few simple examples. Let's suppose that we have the null sequence, so the sequence of all zeros. Well, and this is for every n natural number. Well, then of course Sn, which is the sum for k that goes from 0 to n of ak, of course this is 0. And it is clear that the limit as n goes to infinity of Sn, of course, is 0, which is nothing else than the sum of the series. Okay, this is quite trivial. Let's go to another example. Let's consider now the sequence of all ones okay, for every natural number n. Well, then we can say that Sn, right, which is the sum k goes from 0 to n of ak. Well, let's see what we get. Well, we get, of course, 1 that corresponds to k equals 0. We have 1 that corresponds to k equal 1 plus ... 1. So we have n of this plus the 1 that corresponds to k equals 0. So we can definitely say that this is basically n plus 1. Now, if we establish the limit as n goes to infinity of Sn, clearly this limit is plus infinity. So we can conclude that the series sum of n goes from 0 to infinity, diverges, and we just say that this is plus infinity to say that this series diverges to plus infinity. As a side note, we can define the partial sum also starting from a number different from 0. So, for example, another example of partial sum is the following. Sum ak for k that starts from 15 and go up to n for some n, of course, which is larger than or equal to 15. So this would be a15 plus a16 plus ... up to an. And now we have a first important theorem. Suppose that we have the two real sequences an and bn that are equal definitively. Okay, so from some n0 onwards, the terms of the two sequences are equal. So this is what being equal definitively means. Okay, now if this is the case, we can conclude that the sum of ak and the sum of bk, so basically the two series, okay, that are built on top of these two sequences have the same behavior. So let's give a proof of this theorem, which is going to be quite straightforward. Okay, we'll provide only a sketch of this proof. If the two sequences an and bn are equal definitively, the partial sums Sna and Snb only differ by a constant, since we can only have a finite number of terms in each partial sum which is different. Okay, so the difference between the partial sums can only be a constant, but this doesn't change the nature of the limit. So therefore, if Sna tends to some limit L1 into the real numbers, then also Snb tends to another limit L2 into the real numbers. It can happen that L1 might differ, okay, from L2, but this doesn't change the fact that the two series are both convergent. Same story if Sna diverges to plus infinity, then it must be also that Snb diverges to plus infinity. If S and A diverges to minus infinity, the same must be happening also for S and B. And if S and A has no limits, then also S and B has no limit. So this way we have proved that if AN and BN are two real sequences that are equal definitively, therefore the series sum of AN and sum of BN have the same behavior. So this is the behavior 1, behavior 2, behavior 3, and behavior 4. Let's conclude with an observation which might turn out to be useful in the future. Observation. In a series, we can change a finite number of terms without modifying the behavior of the series. And this is clear because we, as we just proved, by changing only a finite number of elements in the a real sequence AN, and of course that implies also changing a finite number of terms in the partial sums, doesn't change the general behavior of the sequence. Let's consider now a first important class of series, which are the so-called telescopic series. And the first telescopic series that we will consider is the following. Sum n goes from 1 to infinity of 1 divided by n squared plus n. Let's evaluate a few terms of this sequence. For n equal 1, we have 1 divided by 2. For n equal 2, we have 1 divided by 6. For n equal 3, we have 1 divided by 12, and so on and so forth, right? And notice that we can also rewrite this if we just reconsider the general term, sum for n that goes from 1 to infinity of 1 divided by n times n plus 1, we realize that we can also rewrite this as 1 divided by 1 times 2 plus 1 divided by 2 times 3 plus 1 divided by 3 times 4, and so on and so forth. Okay? Now, let's make some tests and see what happens with the first partial sums, because remember that the procedure is the following. The procedure is from AN evaluate the partial sums and then evaluate what is the limit of the partial sum. Okay? So let's write the partial sum S1. Okay? Well, S1 is the sum for n that goes from 1 to 1 of AN, right? Which is like saying 1 divided by n times n plus 1. And of course, this is simply 1 over 2. Let's consider now S2. Well, for S2, we have 1/2 plus 1/6. And this is 2/3. And notice that 2/3 can also be written as 1 minus 1/3. Okay? So I will put this result here, because also 1/2 could have been considered as 1 minus 1/2. Let's proceed with S3. S3 is equal to 1 over 2 plus 1 over 6 plus 1 over 12. Okay, and if we write a common fraction, we have 6 plus 2 plus 1, right? Which is 9 divided by 12. Again, this is 3 divided by 4, which we can write as 1 minus 1/4. So at this point we can make a conjecture. What is the conjecture that we're making now? Well, the conjecture is that Sn would be equal to 1 minus 1 over n plus 1. How can we prove this conjecture? Well, we can prove this by induction. Proof by induction. Let's see. Well, we have the base case, and the base case is that S1, which is given by 1 minus 1 over 2 by the formula, this should be equal exactly to what we have found, which is 1/2. So of course this is easily verified. Now let's go to the induction step. Well, the induction step is the following. If we assume that Sn is equal to 1 minus 1 over n plus 1, we should see that Sn plus 1 is equal to 1 minus 1 over n plus 2. Okay? So let's prove this. From the induction hypothesis that Sn is equal to 1 minus 1 over Sn plus 1, well, Sn plus 1 should be simply Sn plus, well, the next term, but the next term should be 1 over n plus 1 times n plus 2, right? So let's replace Sn with 1 minus 1 over n plus 1, and then we sum 1 over n plus 1, n plus 2. And this is now equal to, if we take a common denominator, n plus 1, n plus 2, we have 1 minus n plus 2 plus 1. We need to have n plus 1 times n plus 2 minus n plus 2 plus 1. Okay, let's proceed with this expression, and let's expand the products at the numerator. We can leave n plus 1, n plus 2 at the denominator, and on top we have n squared plus 3n plus 2 minus n minus 2 plus 1. And we see that, of course, we can simplify 2 and minus 2, and this becomes now n squared plus 2n plus 1 divided by n plus 1, n plus 2. But notice that the numerator is nothing else than n plus 1 squared divided by n plus 1, n plus 2. And we can simplify this and this, so we have n plus 1 divided by n plus 2. But again, this can be re-expressed as n plus 2 minus 1 divided by n plus 2, or if you like, 1 minus 1 divided by n plus 2. And this will conclude the proof. So yes, we can definitely conclude that the conjecture was correct. So we can reuse this expression and evaluate the limit of this expression. Okay, so we can just write that the sum, we notice that for n that goes to infinity, this goes to 1, so we can conclude that the sum n goes from 1 to infinity of 1 divided by n squared plus n, which is, if you like, the sum n goes from 1 to infinity of 1 divided by n times n plus 1 is just equal to 1. Another example of telescopic series is the following. Sum n goes from 1 to infinity of the logarithm of 1 plus 1 over n, which we can also rewrite as sum n goes from 1 to infinity of the logarithm of, we have with the common denominator, we just have n plus 1 divided by n. Okay, so also in this case, let's see what the partial sums look like. If we evaluate S1, we have the logarithm of, we have just the first term, right? So 1 plus 1. So this is simply, or if you like, we can rewrite this by just using the second expression. We have 1 plus 1 divided by 1. So this is just the logarithm of 2 divided by 1. If we evaluate the S2, well, in that case we have the logarithm of 2 divided by 1 plus the logarithm of 3 divided by 2, right? Which, by applying the properties of the logarithm, we know that this is logarithm of 2 divided by 1 times 3 divided by 2. So this turns out to be simply logarithm of 3. Okay, so again, we can make a conjecture. I think we are ready to make a conjecture about Sn. We can say that Sn is nothing else that the logarithm of, sorry, this was the logarithm of 3. Okay, so we have the logarithm of n plus 1. Okay, so this seems quite intuitive, right? Why is that? Because you see that up to n, if we use the properties of the logarithm, all the terms multiplies out and they will simplify, and the only thing that we are left at this point is the last element. In this case is 3, and in general this will be n plus 1. Okay, now I think this example shows clearly why we use the term telescopic, okay, for the all these series. Let me go back a second to example 1. You remember, so this is example 2. This was the example 1. Okay, so in this case we had the series, well, the sequence was 1 divided by n squared plus n, which we wrote as 1 divided by n times n plus 1. But we can express this as 1 over n minus 1 divided by n plus 1, and you can easily check this. Okay, so this is, we can express the single term of the sequence as a difference of two sequences. So when we write Sn, well, for the n equal 1, we have 1 over 1 minus 1 divided by 2. Okay, so this will be a1 plus, let me go to a2. Well, a2, this will become 1 over 2 minus 1 over 3. Then we have 1 over 3 minus 1 over 4, and so on and so forth. So you realize that we can have all the elements of the sequence in the sequence that they can cancel out each other. So this will leave us with basically only the first and the last term of the partial sum. So we have 1, because of course this will remain 1, and we have only the last one that will remain, which will be 1 minus 1 over n plus 1. Okay, so if we go back now, and so this is the effect of telescopic series, that basically we are compressing the entire partial sum between the first and the last element. If we go back now to example 2, let's see if this same process applies also to the series of the logarithm. Okay, so we have that the logarithm of 1 plus 1 over n, which we wrote as logarithm of n plus 1 divided by n, okay, and we just said that, well, of course this can also be expressed as the logarithm of n plus 1 minus the logarithm of n. So once again we have that the general term of the sequence can be expressed as a difference of two sequences. So if we evaluate the partial sum as n, well, we first need to evaluate a1, then we'll have a2, then we'll have a3. Let me start with a1. Well, a1 will be logarithm of 2 minus logarithm of 1. a2 will be logarithm of 3 minus logarithm of 2. a3 will be logarithm of 4 minus logarithm of 3. And we see immediately that logarithm of 2 and minus logarithm of 2, they will cancel out. And the same happens for logarithm of 3 and minus logarithm of 3. So even in this situation, we realize that the only terms that will survive is only the last one, which will be exactly logarithm of n plus 1, and there will be this term that will survive, minus the logarithm of 1. However, the logarithm of 1 is 0, so we can conclude that this is simply logarithm of n plus 1. At this point, it is easy to see what is the sum of the series. The sum of the series will diverge. So we can easily say that, because if we evaluate the limit as n goes to infinity of Sn, which is nothing else than the sum of the telescopic series, this is the limit as n goes to infinity of the logarithm of n plus 1, which is of course plus infinity. So the series sum of logarithm of 1 plus 1 over n goes from 1 to infinity. You see, I'm starting from 1, not from 0, just to avoid any problem with these elements. This is divergent to plus infinity. Another very important class of series is the class of geometric series, which are series of the form sum n goes from 0 to infinity of a to the n, which is a to the 0 plus a to the 1 plus a to the 2 plus dot dot dot. Now we assume by convention that a to the 0 is equal to 1, and this is also valid when also if a is equal to 0. So what we are saying is that by convention we consider also the case where we have 0 raised to the 0, which would be an undeterminate form, to be equal to 1. So this geometric series will take the shape 1 plus a to the square plus a to the cube with all the infinite powers of a. Now, what we need to study this series is a formula that we proved right at the start of the course. We proved that the partial sum of a geometric sequence is given by, so the sum k goes from 0 to n of a raised to the k is given by a fraction a raised to the n plus 1 minus 1 divided by a minus 1. We proved this by induction, and this is valid for every n into the natural numbers and for every a different from 1. Notice that, just let's make a notice, for a equal 1, well, in that case we have that Sn would be simply what? 1 plus 1 plus dot 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 plus 1. So it would be 1 plus n, which clearly is something that will tend to plus infinity. So for a equal 1, we already know that the geometric series will diverge to plus infinity. Okay, so this is a result that we might reconsider later. However, from now on, let's see what is the different behavior of a geometric series depending on the value of a. Let's make just a representation here of all possible values of a. So we saw that if we have a equal 1, well, in that case we have plus infinity. Okay, now let me consider the situation where a is larger than 1. Well, if a is larger than 1, Sn would be equal to 1, because this is a to the 0, plus a squared plus dot 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 a to the n. And I mean, it is easy to see that this will diverge to plus infinity. So we can conclude that in all cases where a is larger than or equal to 1, so if a is equal to 1 or if a is to the right of 1, we always have a geometric series which is divergent to plus infinity. Let's now consider the situation where a belongs to the open interval minus 1, 1. So we are now considering this interval. Minus 1, 1. And we are looking at these possible values for a. Now, remember that we know that Sn, of course a is different from 1, so we can reuse the formula for the partial sum, which is a raised to the n plus 1 minus 1 divided by a minus 1. And we would like to see what is the limit of this sequence. Now notice that the absolute value of a raised to the n plus 1, okay, you know why I'm considering the absolute value? Because a could be possibly negative, and we want to get rid of the problems with the sign. So let's evaluate this, which is nothing else than the absolute value of a raised to the n plus 1. And now we know that the absolute value of a is a positive number between 0 and 1. Extremes excluded, and we know that this of course is something that will go to 0, and by the theorem of absolute convergence of sequences, we can conclude now that a to the n plus 1 will go to 0, and these in turns imply that Sn will tend to what? To minus 1 divided by a minus 1, or if you like, 1 divided by 1 minus a. So we can conclude that in this interval, the limit is always 1 divided by 1 minus a. Okay, now it's time to consider what happens if a is equal to minus 1. Well, in that case, let me consider the different values of s. Let's make a test, okay? S1, of course, is going to be 1 because this is minus 1 raised to the 0, and we know that this is 1. Then we consider S2. S2 is equal to minus 1 to the 0, which is 1, plus a, which is minus 1, so this is 0. Let's consider S3. S3 is 1 minus 1 plus 1, because once again we have minus 1 raised to the square, which is 1, and we have 1. So clearly we have a sequence 1, 0, minus, 1, 0, 1, and this has no limit. We might also consider the case where a is less than minus 1. So let's now consider the last case where a is less than minus 1. Well, if we look at the expression of the partial sum, we have a to the n plus 1 minus 1 divided by a minus 1. We clearly see that this sequence of partial sums can diverge to plus or minus infinity depending on the exponent to be even or odd. So let's consider the two subsequences, s2n and s2n plus 1. Well, in this case we have a to the 2n plus 1 minus 1 divided by a minus 1, and in the other situation we have a to the 2n plus 2 minus 1 divided by a minus 1. And we immediately see that the first subsequence will diverge to plus infinity because we have that a raised to the 2n plus 1, of course this will go to minus infinity, and this will be a number less than 0, so clearly the ratio is going to go to plus infinity. Instead, in the other subsequence, we still have, of course, this that is less than 0, but this will now diverge to plus infinity. So the ratio will diverge to minus infinity. So there cannot be any common limit because these two subsequences have different limit. So we can conclude saying that there is no limit. So we can go back to our previous picture and conclude that in all these situations where a is minus 1 and to the left of minus 1, there will be no limit. So in conclusion, for the geometric series, we can summarize our result as follows. We can say that the sum n goes from 0 to infinity of a raised to the n is equal to plus infinity if a is larger than or equal to 1. 1 over 1 minus a if a belongs to the interval minus 1, 1, and no limit if a is less than or equal to minus 1. And this is what we need to remember for the future. We will be using this geometric series in many occasions. The last properties we would like to explore are some algebraic theorems on numerical series. So let an and bn be two real sequences. Then we can say that the sum as n goes from 0 to infinity of an plus bn is equal to the sum as n goes from 0 to infinity of an plus sum as n goes from 0 to infinity of bn, except when on the right hand side we have the undetermined form of the types infinity minus infinity. Well, in that case we cannot use this theorem. Or if sum of an and or sum of bn have no limit. So we must assume that the single series sum of an and sum of bn, they have a limit. This limit can be finite, can be plus or minus infinity. So in that case we can use the theorem. Otherwise, if at least one of these two series have no sum, has no limit, we cannot use this theorem. The second algebraic property is exploring what happens when we multiply a series by constants. So let's say that the lambda is a real number different from 0. Then we can say the sum as n goes from 0 to infinity of lambda an is simply equal to lambda times the sum n goes from 0 to infinity of an. So we can basically factor out lambda from the series itself. And the third property is, well, it says that we cannot take any conclusion when we multiply out the two sequences. So if we have the sum as n goes from 0 to infinity of an times bn, we cannot say that this is equal to the sum of an times the sum of bn, except only very specific cases. So this is in general not true, right? And notice that as a note here, this is not true even if an and bn are definitively 0. So what I'm saying is that we would expect now that, for example, we have a0, a1, a2, and after 2 we have 0, 0, 0, 0, right? And on the other side we have b0, b1, b2, b3, and then we have 0, 0, dot, dot, dot. So we might think, okay, because after n equal 3 or n equal 2, from this point on, right, from this point on, the product is going to be 0, 0, 0. We are just left with the limited number of products. So, but even in that case, we cannot say that the sum, we cannot say that the sum for n that goes from 0 to 2 of an bn is equal to the sum as n goes from 0 to 2 of an times the sum as n goes from 0 to 2 of bn. This would be false. In fact, let me consider also, this is not even true if we stop at 1. Let me do this. Let me stop at 1 here. So what do we have? Well, we have that a 0 B0 plus A1 B1, right? But this is not like having A0 plus A1 times B0 plus B1. In fact, we have missing mixed terms. In fact, what we have here is A0 B0 plus A1 B1, but then we have A0 B1 and A1 B0. So this goes with this goes with this, but we still have these terms that are missing. So in general, we cannot apply this theorem with the product. Okay, now let's give the proof of the first theorem. Okay, so we want to prove that the sum of an plus bn is equal to the sum of an plus the sum of bn. How can we proceed? Well, the easiest way is just to consider the new sequence Cn equal to an plus bn and consider the partial sum. What is the partial sum up to n of this sequence C? Well, this is A0 plus B0 plus A1 plus B1 plus dot 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 up to AN plus BN. But by the associative properties, we can write this as A0 plus AN plus B0 plus Bn, and this is SNA plus SNB. And now, when taking the limits of S and C, as n goes to infinity, which is, by the way, nothing else than the sum of an plus bn, well, this would be, by just applying the algebraic theorems of the limits, this is just the limit. Also, the proof of the second theorem is straightforward. Remember that the second theorem says that if lambda is different from 0, the sum of lambda an is just equal to lambda times the sum of an. Well, what can we do now? We just take the sum of lambda ak for k that goes from 0 to n, which is basically the sum of up to n, right? But this is what? This is lambda a0 plus lambda a1 plus dot 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 up to lambda an. But of course, this is nothing else than the lambda times the partial sum of the sequence A. And when we take the limit of lambda s and a as n goes to infinity,